Thanks. So I'm Neeraj Gupta. I run our advanced development group at Sierra Nevada Corporation, where we're working through the next step contracts as Brent mentioned. So what I'm going to talk about is our flexible and modular architecture to the gateway. So I'll start by saying we've had a couple contracts through NASA to look at the architectures for the next step. Two program and really focused on the gateway architecture. So the first being what's called Appendix A, the habitation systems. It's actually a little bit more than just the habitation system itself. So the habitat in our system up there is the large inflatable looking piece there. But it's more than just the inflatable portion. It's actually the entire architecture. So we're looking at how you put up each one of these modules, what each module would do, the functions, the operations on orbit. Also the launch and flexibility of launch scenarios, what types of launch vehicles you would go on and how you would put all of these things into orbit. The third piece of the contract is actually to look at a prototype, is actually to develop a ground prototype for the system. So what we decided to do is to build a full-scale ground prototype of what we call our LIFE, our large inflatable flat fabric environment, which is the large inflatable portion, as well as what we could call our LCM, our logistics control module. It's part of our PPE concept, for those familiar with the power and propulsion element. So we are actually building a full-scale ground version of this in our location in Louisville, Colorado. And just to give you an idea of the size, the inflatable itself is 8 meters diameter by 6 meters long. In U.S. English units that I would go by, 27 feet diameter by 18 feet long, just to give you some context. So it's quite large. It's over 370 cubic meters of habitable space total in the entire architecture. The second study we had is a next step Appendix C, which is specifically focused on the power and propulsion element. So that concluded earlier this year, as I think most folks are aware. This will be the first element of the gateway and is going through the solicitation process as we speak. But we developed or evaluated the power propulsion element in more detail through that study. So there were a total of 18 study topics. There were 23 in total. We looked at 18 of them in depth and looked at how our approach to PPE meets those different objectives. So here's our overall concept, and what you can see is it's really a flexible and modular architecture. That's our tenet to this entire system. We think that is one of the most important pieces to the gateway, and I'll talk here in a few minutes about some of the iterations that have gone through on the gateway. So what we're looking at is flexibility across the entire architecture. So not only the elements itself, but also how you launch and how you operate on orbit. So you can see that we have multiple different elements throughout the system. But one of the other things we wanted to hold as being extremely important is flexibility in getting each module up. So we held that each one of these elements should be able to go on not only an SLS flight, but any commercial ride as well. And that gives you additional flexibility throughout the buildup of the gateway. It is a building block approach, so you can think of these as almost tinker toys that you can rearrange and reassemble in orbit. All of them are docking style attachments. So there are a lot of different scenarios that we've played out, one of which you see up here. This is one of multiple configurations we've looked at that allow for all of these elements to be basically reconfigured on orbit as you need. So as Orion comes up, it can dock with certain locations. As cargo and logistics come up, they can also be flexible throughout the system. And we look at the system as being the first instantiation of the system. And what I mean by that is, just like ISS, it morphed over time. The very first versions of ISS is not the final version that we see today. There was additional modules and additional capabilities added throughout the lifetime. And we expect that to happen here on the gateway as well. So the other thing that was at the very beginning, one of the focuses was looking at a transport for long durations missions, human missions. So Mars class type missions and asteroid missions. And so one of the things we've always kept in the back of our minds is this capability of making a deep space transport at the gateway itself. And so with that in mind, you can see some of the architecture is built around that. Our large inflatable, for instance, it's not only useful for the gateway, but it is also useful and meets all the requirements for something on the order of 1,000 or 1,100 day mission to Mars. And so we've kept those in the back of our mind to make sure that we are not only focused on the gateway itself, but looking at what may be next and how we can utilize this platform to really help what's coming up next. I'll quickly go through some of the elements of our gateway. On the left-hand side, you can see a picture of the entire buildup. And as the design has evolved over time, there have been new elements added in from what we started with a handful of years ago. And so you can see our concept uses a PPE on the left-hand side, an international habitat in the green in the center, life, which is our inflatable habitat, and then down at the bottom you can see locations for a spree, which is can be used for refueling and science payload operations. What we call our ELCM. Our ELCM is our Extended Logistics Control Module. The purpose of that is a handful of things. So one is to bring logistics to the gateway. So as you're building this up and as you have these different 30-day human-tended missions, there's logistics that needs to go up in certain orders. So between things like our PPE and our ELCM and the launch of the habitat itself, we're able to provide all the logistics necessary for the gateway. And then lastly, you also see a second PPE listed as PPE 2 here at the bottom. We think there are quite a few major benefits to having multiple PPEs as part of the system. It gives a lot of additional flexibility to your operations. Since it is the main power and propulsion, it augments those at certain times during the mission life. So there are a lot of really interesting benefits to having a second PPE. As I said, all of these are docking compatible, so there are 3 IDSS ports for Orion and other visiting vehicles, be it landers, be it ascent vehicles, whatever it might be. We do have the capability of docking to all of those. And we are leveraging all of the systems that are currently in development at SNC. So I think many people are aware of our Dream Chaser program and all of the components that are going into that system. You can see both the shapes of the ELCM and the PPE resemble what is on the back of our Dream Chaser, the cargo module portion. So both of those technologies are derived off of that technology and utilize a lot of the same subsystems and hardware that we're using within the Dream Chaser program. Additionally, we have two major partners that we're working with, Aerojet Rocketdyne, and using their thrust capability, their AEPS thrusters, and the large inflatable is actually provided by ILC Dover. For those of you familiar with ILC, they do a lot of work in soft goods, from spacesuits to surface habitats and so forth. So throughout the project, it's been an interesting roller coaster ride from where we started a few years ago to where we are now. NASA has thrown us curveballs along the way, and I think they just want to see how we react. So we started way back when we originally proposed this with Mars as being the focus, and the moon being a stepping stone within. And obviously, as we've gone through, the moon has become much more the focus of the gateway. We fully support that and understand why the transformation. But one of the other things that happened is there was a change in number of elements. Went from 4 elements to 7 elements in the current version. A lot of international cooperation as well. So as it's changed, we've changed. And so we've iterated through this design. You've probably seen a lot of these different things through different press releases and so forth that we put out on concepts. That's one of the major reasons for the change, is that every time NASA changes, we want to make sure that we are evaluating our architecture and seeing how we fit into it. So we started with these concept up in the top left, and currently are the concept on the top right. And you can see there's different orientations of these as well. There's straight line configurations, things coming out of plane. We've looked at all kinds of different things, from access of EVAs to assembly to safe havens with Orion and what kind of operations you might do. And actually through all of these iterations, we've developed a tool set that allows us to evaluate basically any modification or any configuration of the gateway that may come about. And so through it, every time that NASA has come up with a different version or new modules, we put up ours on a board and say, are these the right modules? And every single time we've come back and said, these three different platforms can satisfy every one of the requirements that have come out, and can accommodate additional elements, as you saw from the Spree and the International Hab, and still preserves all of the things necessary for a deep space transport mission. Oh, that's it.
Thanks, Neeraj. As I said at the beginning, we'll go to the second talk now, and then after the first three, then we'll have a set of integrated Q&A. Okay, so next up is Mr. William Pratt from Lockheed Martin Space Systems Company. And the talk is Lockheed Martin Next Step 2, Habitation Study, Cislunar Gateway Architecture Status, and Results to Date.
And real quick before I start, does the audio work? I do have a video in here.
Should work.
Okay, we'll find out.
We'll find out. And we have help if it doesn't.
Thank you.
So.
All right, we'll try to wake everyone up. Okay, yes, thanks for the introduction. My name is Phil Pratt. I am the program manager at Lockheed Martin in Denver, Colorado, for the Next Step Habitation Study. And I thought I would just give a brief kind of summary of where we're at, and then talk a little bit about the gateway in general and the partnership that we have with NASA on Next Step and the kind of things that we're working on. So it's just kind of a collage, some baby pictures here of the things that we're working on. As the previous presenter mentioned, we have kind of a mix of work that we're doing actually under the Next Step contract with NASA. The first big one is what we call concept refinement. So that's a lot of the architecture work and looking at, again, the different modules that we think we need to have sort of a minimally functional gateway, and then which order you want to launch the pieces, and then also some of the standards and interfaces. I like to think of the gateway as a collection of Lego bricks, and so you want to make sure that all these bricks are going to plug together, and the standards work is a big part of that. So in addition to that, though, we have prototypes that we're building. So here on the left, if we have any Italians in the room, you might recognize that as Donatello. It's one of the 3 MPLMs that actually is space rated. This one did not fly in space, but the other 2, Leonardo and Raffaello, did. Leonardo is also known as the PMM. That was left on station and is used for storage. But NASA loaned us one of the MPLMs, and actually that serves as the basis or the foundation for the prototype that we're building. Right now it's at Kennedy Space Center. It will stay in Kennedy Space Center at the space station processing facility. And work is underway right now to retrofit that and basically modify it so that it represents our concept. And then just some other pictures here. We also have another prototype we're building. It's an avionics and integration lab. That's at near Johnson Space Center in Houston. And if you can imagine, as folks have said, the gateway is what we call crew tended, meaning astronauts do not stay there year round. They come up for maybe 30 or 60 days each year. And so when Orion is not there, the power and propulsion element is really, at least in our minds, the brains of the operation. And then when Orion comes up, it takes over more command deck features. And so what we want to do is do a lot of risk reduction now and help NASA understand how to get the moding to work correctly between Orion and the rest of the gateway when it comes up. And so that's the main focus of the avionics lab. We also do a lot of work with artificial and virtual reality. I'll show a little bit more of that later and talk some more about it. We're also looking at EVA modules and studying what we think is the best way to construct and build an EVA module for the gateway. Okay, so I thought I would start sort of with at least Lockheed Martin's vision for the future at the moon. And so starting here in the upper left-hand corner with the ISS and stepping out towards the moon, and then also beyond to Mars, which I thought was in here. Yeah, there it is, right here in the picture. And so, you know, this even just a couple years ago seemed like science fiction, right? You've got landers and rovers on the surface of the moon conducting commercial activities, launching payloads. This sort of looks like it's attacking the gateway, but it's not. It's returning a payload from the surface of the moon up to the gateway, where it is then taken by Orion back to the Earth. So if we keep in mind that this is sort of the future that we're all working on sort of in an international sense, then where does the gateway fit into that? The gateway is a huge enabler for this as a waypoint. I like to think of the gateway as an airport or a train station around the moon. It's the place where we'll go. We'll park logistics there, where other things can come and go, where we'll stash samples that we bring back from the moon, propellant perhaps, and other logistics that are needed to go to the surface. And so from our standpoint, there are a few elements now that I think you've seen multiple architectures with different elements. This is just sort of a notional set of elements, but of course you have the Orion here in the bottom left. That's sort of the workhorse, brings a lot of cargo element, or not cargo necessarily, but habitat elements to and from the station. Also brings the crew to and from the gateway as well. And of course the Orion is both a US and international endeavor, right? Airbus, or ESA, is actually the one that's building the European service module. Cargo and logistics, we imagine that as being US or internationally provided. Here we're just showing a notional cargo pod that could bring cargo to and from. And then a couple of habitat modules, so maybe one US domestic module to start with, and then an international habitat as well. We strongly feel there needs to be more than one when you start to look at all of the functions that you need, even when you're only doing missions of 30 to 60 days. We feel like you need at least more than one, at least two halves. And then of course EVA for spacewalks, and then the power propulsion element, which is really the power station and the communication station. Okay, here's a quick video that we put together of a notional sequence. It has narration, so be glad. know, my boss is a former astronaut, and he pointed out to me, that's a really sporty maneuvers going around the gateway, but I think you understand it's just notional. Okay, so in terms of living and working in space, here's just sort of a cutaway image of what the inside of a gateway might look like. You can imagine here, we're showing 3 of the astronauts here, the 4th one is probably hiding from the other 3 somewhere, but it's not, we like to say this is not ISS 2.0, right? We can't launch something as large as ISS into cislunar, even though we're taking a lot of the lessons learned from ISS certainly forward. We have to make better use of the space that we have and be a little bit more efficient with it. So we're looking at things like making sure that the habitat modules are reconfigurable and scarred for multiple purposes, because the gateway will evolve over time. Habitat module functionality will shift over time. So how do we ensure that that's possible? And of course, up here with the Orion, early on in the gateway buildup, Orion actually is a very capable, advanced human spacecraft that's designed for deep space, with things like command and control, crew interfaces, life support, power propulsion. All of those things are things that we can rely on early on in the gateway as the gateway becomes more self-sufficient. Okay, I just mentioned this. So the functional allocation between the different modules is really critical to getting this right. And when you add in the international component to that, making sure it just adds a layer of complexity, right? So making sure that the functionality across them is agreed upon early on when you're building this is really important, especially when you only get 2 or 3 habitats to do it in. So this is just sort of also notional, but we look at things, all the different activities that the crew might be performing on board the gateway, and then we try to make sure that we don't, for instance, have the toilet next to where the crew is preparing the food, right? So you just try to look for logical overlaps between functions, and we don't want the crew sleeping right next to the exercise station, things like that. Okay, so I've sort of touched on this a little bit, but when you think about the track record that humans have in space, right? We at the ISS have experiences of a year or more in LEO, but essentially you can push the button and come home within a couple of hours. We also have limited experience at the moon from the Apollo missions, but again, those are pretty short durations. So when we start to think about what we need to do in order to get both to deep space around the moon, but also onto Mars, it's really about increasing autonomy and making the crew more autonomous. And so that's a lot of what we're looking at as part of our gateway study. Okay, and so one of the things we announced earlier this year is Maya. Maya is a model-based artificial intelligent assistant, and really it's what we call a digital twin of the spacecraft. So one of the ways we think we can increase the self-reliance of astronauts is through things like digital twins, which are complete onboard virtual or digital representations of the spacecraft and its environment. And it's one of the really cool things about this is digital twins are not necessarily new. They're throughout lots of different industries. But in this case, we're putting that in the hands of the astronauts on board the gateway so that they have access to all the information real time, and that really helps them deal with the delay. You can't replace the hundreds of geniuses that are on the ground helping the astronauts, but you can give them the ability to troubleshoot problems when they're time critical. Okay, real quick, so the gateway, one of the unique things about it, again, is that it's crew tended. So the different modes of operations are really interesting. The gateway and the crew configuration will use a digital twin to do things like supporting troubleshooting and reducing crew workload. And then in the uncrewed situation, we actually want the gateway to still provide useful science and engineering. And so crews on Earth will actually be able to interact with the gateway robotically or even autonomously, and all that will be done through the digital twin. Okay, and then I think the last chart I have is a video here. This is actually of some work that we did at our lab in Denver, just illustrating the idea of telerobotics on the gateway. So this is real time. We tried to sync the videos up, but the gentleman in the upper right, through virtual reality, is actually operating the robotic arm on the bottom left. which is in our Gateway mock-up in Denver. So we've been able to show this remotely across the country, and you can see he's got a stereoscopic image of the actual environment here. And so this is just sort of a mock-up plant experiment where he's taken soil samples. This really increases the utility of the Gateway when humans are not there, which I think is a really important feature. Okay. And that's all.
Okay, thanks, Phil. Next up is Mr. Sam Wall from NanoRacks with Ixion, a wet lab habitat platform for LEO and the Deep Space Gateway.
We'll go with that. Thank you all. Good afternoon. I'm Sam Wald, Senior Engineer at NanoRacks, and thanks to the Space Architecture Technical Committee for hosting this. So today I'm going to talk to you about what used to be called Ixion has been now renamed to Outpost. So we put the abstract in before we renamed it. And you know, we've been talking a lot. The first two talks have been about what we're going to be doing in cislunar space at the Gateway. And at NanoRacks, you know, we're interested in what's going to be going on at LEO while this Gateway is also developing, and how we can help build up low Earth orbit capabilities as well. So NanoRacks is a commercial services company for customers on the International Space Station. So we help enable people to perform research and to operate in space. So we have internal platforms and external platforms where we host payloads from universities, companies, and even elementary school students. We also deploy satellites from the International Space Station, as well as operate payloads from our Houston Operations Center. We've been following the market demands and have recently invested in the Bishop Airlock, and you may have seen it downstairs in our booth. And that'll be on the space station next year. And finally, we also support customers getting payloads on suborbital flights with New Shepard. So really the question is, with all this activity going into the Cislunar Gateway, and based on what we've learned on the ISS, how can we take these capabilities and keep providing them to our customers in an efficient manner in low Earth orbit? And so we've teamed up with NASA, as well as our partners Maxar and ULA, on the NanoRacks Outpost program, which I'll describe now. And this is supported by NASA's Next Step 2 public-private partnership program, which has also supported these other companies that you've seen. So the overall architecture of the Outpost program is based on the reuse of upper stages. So we've partnered with ULA, who currently launches the Delta IV and Atlas V launch vehicles, and is now working on the Vulcan launch vehicle, which I believe was described in a few presentations. And so, as you can see here, there are really three main components: the mission module, a node, and what we're calling the XHAB, which is in fact a repurposed upper stage of the Vulcan launch vehicle. So it's a Centaur 5-meter upper stage. So this is based on what many have called a wet hab or wet lab architecture, where this portion of the vehicle contained fuel and is vented on orbit. And because this vehicle is based on liquid oxygen and hydrogen, it's very easy and has been performed in orbit to vent the tank, so we have a nice open volume. These other portions, the node and the mission module, are essentially the payload of the upper stage for the launch. And actually down here, you can see an overall view of the Vulcan vehicle with the upper stage here, and then the node and the mission-specific mission module on top. So how are we going to convert the tank? We spent last year finishing a phase 1 feasibility study for NASA, and it ended last year, where we worked out some of the details and trades we would need on, is this really possible? So here you can see for the tank conversion process, really the thing that has enabled this and what has made it different than when this was tried in the past, you may not recall, but the Skylab program is really some of the robotic capabilities that we now have available to us, where EVA would have been required before. So we're going to plan on robotically cutting and opening the tank after it's vented, ingressing the tank with that robotic system, and plugging this internal volume, the fill and drain valves, with epoxy. And that will give us essentially a sealed pressurized volume to begin to outfit. There's compressed air stored as well as all of the subsystems up in the mission module, which I'll describe in a second. So once the tank is empty and it's been inspected by the robotics, we begin to install the outfitting systems, and we still have a few options for this, and we've partnered with some commercial companies who are developing both inflatable and assemblable components for outfitting. And this outfitting essentially provides the interface to the integrated subsystems and also provides crew accommodations and functional areas for the crew. And in order to save crew time, it's also being designed to be compatible with the robotic systems that Maxar has developed for their Dragonfly spacecraft assembly program. Inside there's also an airlock, which is used for EVA, and that's pre-integrated on the ground as part of the node, as well as all of the other subsystems in the mission module. So there are some external modifications that are required for this architecture on the ground. So we can't, in this case, we're not just taking an upper stage as is and converting it, but it was deemed last year that these changes to the vehicle are feasible, and we work with both the launch vehicle and the subsystem providers on what those interfaces are between the two. So we'll just run through them here. So the first change is we're going to be mounting layers of multi-layer insulation and MMOD micrometeoroid orbital debris shielding onto the vehicle on the outside, and that's cinched down during launch and then deployed on orbit to provide the depth that's needed for protection and for thermal insulation. Solar arrays, because we're already deploying, we're already adding another structure on the outside, we decided that it was actually less complex to just add the solar arrays as body mounted as well. And that also allows us to not have arrays in the way of docking vehicles and other EVA and robotic activities on the exterior of the vehicle. There's also a body mounted radiator pre-integrated on the node section of the vehicle, as well as low profile grapple fixtures for the robotic arm to be able to operate on the outside of the vehicle. And this arm, actually, its geometry and its actuators were designed such that it can move in and out of the airlock. So, although we focused on ULA, we partnered with ULA and we've been focusing on the conversion of their vehicles. We're also interested in, what are the other vehicles available to create an ecosystem of platforms for multiple types of uses. This vehicle, based on the Centaur 5, is compared to the other configurations we've looked at, is fairly large. And we're interested, and we think there are some business cases where we might want to look at more minimal platforms and even potentially completely uncrewed platforms, at least for part of the time. You can also see some vehicles on here which do not exist anymore, just for reference, like the Saturn V and Shuttle. Though interestingly, both of those were considered for wet lab architectures as well.